Thanks for coming back. Hope you enjoyed your coffee. Next presentation is Mr. Roland Nagy.
So, good morning, everyone. My name is Roland Nagy. I'm a PhD student from the Crisis Lab, the IT Security Research Group of the University of Technology and Economics Budapest. And today I will talk about how we are fuzzing trusted applications via shared memory. First, I will talk a bit about trusted applications, what they are, how they work, why they are good for us. Then a little basics on fuzzing, in case any of you is not familiar with it. Then I will tell you how we emulated our trusted application. And finally, how we wrote our custom fuzzer. And before we proceed any further, I must warn you that all that I'm going to tell you today is work in progress. So please tune your expectations accordingly. So first, trusted applications. They are special pieces of software executed by trusted execution environments. They are digitally signed, and of course this signature is verified before execution. And they are isolated from normal world applications, usually by some hardware feature, which in our case will be ARM Trust Zone. And their integrity protection and isolation make them ideal for implementing security-critical applications like certain cryptographical functions, financial applications, or digital rights management related stuff. So, first, ARM Trust Zone. It is a hardware feature implemented in ARM cores, of course. ARM CPUs often contain a register called the Security Configuration Register, which includes a so-called non-secure bit, and depending on the value of this bit, certain memory regions and hardware elements can or cannot be used by the CPU. This is enforced by the system bus. And by the value of this bit, we can partition the execution into a so-called normal world, where we usually have Linux or Android, and a so-called secure world, where is our trusted execution environment, OPTEE. So OPTEE stands for Open Source Portable T. It is ported to more than 50 IoT platforms. And it's mainly an operating system for the secure world, but it has additional components as well. Like it has a driver for the normal world in the Linux kernel and things like that. And OPTEE works in a way that normal applications can request the execution of trusted apps by calling a library function, which will call the T driver in the kernel. Then a so-called secure monitor call will be executed, a context switch happens, and from that point OPTEE will run and it will execute the requested trusted application. And of course, as I said previously, trusted apps are integrity checked and they are loaded to those sections of the memory that cannot be accessed from the normal world. So when we decided to fuzz trusted applications, we had a very specific one in mind, which we developed a little earlier. And we created this to perform rootkit detection checks on the Linux kernel. It consists of several integrity and consistency checks. It's approximately 4,500 lines of C code, so it's a medium-sized project. And it uses 4 services implemented in the trusted kernel. Think of them as something like loadable kernel modules for Linux, except that they are not loadable, but they are compiled into the trusted kernel. And the checks executed by our application can be divided to 3 sections plus an initialization phase. And we plan to fuzz these separately. A bit later I will tell you why. So first we have our initialization phase. Here we compute a set of reference hashes, what we later used by the other sections. Then we check function pointers in the layer called virtual file system of the Linux kernel, which is responsible for hiding differences between file system drivers. Then we check data structures holding information about tasks. Tasks are basically how the Linux kernel sees threads or processes. After that, we have a bunch of general integrity checks, like we check if someone modified the code of the kernel or any of the system calls were replaced and things like that. Then we check files for persistent rootkit components, and finally we have checks targeting various layers of the network stack. So next a bit about fuzzing. Fuzzing is a form of automated security testing, and the basic idea is to execute our application with random or semi-random test cases. It is highly effective because it can be excellently parallelized, and if we have access to the source code, then certain compiler instrumentations can even further improve fuzzing. Of course, it has some limitations as well, like reaching code in many nested ifs, for example, might be complicated, and monitoring the application to detect crashes can be problematic as well, especially in the IoT domain. So I brought this image to explain the general workflow of a fuzzer. So first we have our input files, they are placed in a queue. Then we have our executable, and first we pick one input file from the queue, mutate it somehow, like replace a byte with something random, flip a bit, or append some junk to the end of file, things like that. Then we execute our application with this mutated input. And of course, we monitor it to detect if we could crash it. If we could, then the crash is of course reported to the user, and the input that caused the crash is saved for later analysis. And if the input is considered to be interesting, then it's placed back in the queue and it starts all over again. So, in the image I showed you, it was about how we use input files, but our application doesn't take its input from files, but it reads its input directly from the memory. So the question is how we fuzz this kind of application. Well, we originally developed it in a QEMU-based environment, so we can quite easily manipulate its memory. And the basic idea is, let's just mutate the memory as it is. Well, the problem is that it is used by the Linux kernel, and the kernel wouldn't be very happy if we just started to randomly overwrite things in its working memory. So we would probably have a lot of crashes, and most of them would be irrelevant. So this is not the way. Next idea was to let's fake everything else into another unused region of memory. Like just copy everything and modify the application to read from that. This is feasible, but to do so we would need to change the application a lot. And we would like to avoid that, because the more we modify the application to be testable, the less we actually test the application we want. So, since the kernel is the root of all our problems, then let's get rid of the kernel. Well, the problem is that OPTEE OS, the T running our application, uses the kernel as well, so it wouldn't work without the kernel as well. Also, trusted apps cannot be executed on regular systems for a bunch of reasons, even if we wrote a wrapper to execute it, and even if we executed it on an ARM64 computer, then we still have the problem that it uses custom system calls, like the system calls doesn't match the ones used by the Linux kernel. And here comes Marcel Zeibert's last year Hacktivity talk, where he showed us that it is possible to emulate trusted applications. And to do so, he used an emulation framework called Killing. And that's what we will do as well. So, of course, there are pros and cons of emulation. The pros are that we can execute our trusted app in parts only. It also gives us coverage information regarding what parts of the code we actually executed. And it is quite trivial to identify crashes in this setup, since if our trusted app does something naughty, then the emulation frameworks will simply throw us an exception. Of course, there are downsides as well, like we need to implement a bunch of system calls used by our application. Also, there are the services I mentioned earlier that we use. Those need to be mocked as well. And some library functions will require special attention as well. So with system calls, we are quite lucky, because in Killing it is quite easy to hook them. We just need to implement the desired functionality in a Python function, and by calling another function, we can tell the framework that when this system call happens, I want you to execute this Python function. Here you can see a list of the system calls we implemented so far, fully or partially. In functionality, these vary from logging to session management up to secure storage management. Secure storage is, by the way, a mechanism provided by the T, so the trusted apps can store data persistently in an integrity-protected, encrypted, and rollback-protected way. We use this to store reference hashes, by the way. Then I said we have services used by our application. Well, if we are not running the whole application, but execute it in parts, then we only need to implement 2 of the 4 services. And calling these services are done by system calls as well. So we had to implement 4 commands executed. 3 of them are to produce hashes, which didn't really require much attention because we need to patch these hash checks out of our application anyway. I know I said earlier we don't want to modify our application, but at this point we don't really have a chance if we want to reach code beyond these checks. And the 4th of these commands is to read physical memory, the memory of the Linux kernel. And a bit later I will tell you how we implemented this and why it was a bit tricky. But first, I've said there are some library functions. Well, luckily, when trusted applications are compiled, the functions we used in the code are all compiled into the application, so we don't need to mock any of them. But some initialization needs to be done. Since OPTEE OS is a lot different from other operating systems like the Linux or Android, the implementation of the heap differs as well. In this special case, the heap is actually placed into the BSS segment of our application, which is used to store global uninitialized variables. So when we just simply call malloc, for example, from our application, then it will return out of memory because, as far as it knows, there is no stack, no heap. So we need to tell somehow the application that yes, there is a heap, and it is there in the BSS segment, and please use that. Yeah, we need to call this function to do so. And here, the emulation framework is useful again because it can create snapshots from the execution state of our application. So we only need to perform this initialization once. Then we can execute our application with a random input, and then we can roll back to this snapshot and execute it with a different input. So it makes our fuzzing a lot faster. And finally, how we implemented our fuzzer. So fuzzers need valid example inputs to mutate, like I showed you the files in the example, where we can get a valid example input by dumping a memory image from QEMU, but there are problems with it. First of all, it's too big. Fuzzers don't really like huge input files. For example, the manual of AFL, the most well-known fuzzer, states that please try to keep your input file below 1 kilobyte. Well, with a full memory image, we can't do it. And also, our input file is quite sparse in the nature that we don't read the whole input file, only parts of it. And even from the parts we read, we don't parse all of them. So, as you can see in this image, if we, for example, mutate it here, and we don't read that part of the file, then it was useless. It's like if we did nothing. Then again, if we mutate in a part that we read but do not parse, then again, it was a useless mutation. So we need to handle this problem somehow to avoid a lot of useless work. So mutating the whole input file as one is ineffective. So we came up with a solution to, we take a dump from QEMU, and then we implement our read memory function in a way that it will read the requested data from the unmodified input file, and that will be mutated. But first, we apply a mask on it to guide the fuzzer to avoid useless mutations. And this image is supposed to explain what I've just told. We have our application. It attempts to read this structure from the memory. Then the killing framework takes the execution, reads the requested data from the dump. Then a mask is added to that, and the masked data is given to the mutation engine, which will only mutate those parts that are allowed to be mutated by our mask. So this way we can avoid a lot of useless work. And earlier I mentioned that the killing framework can give us coverage information, meaning that it can tell us which parts of our application were executed. This is useful because this way we can implement coverage-guided fuzzing, where the basic idea is that those inputs that make more parts of the code executed are better because they have a bigger chance to trigger crashes. And here you can see the basic algorithm to implement coverage-guided fuzzing. First, we have a set of interesting inputs, which initially only contains the test cases we added to the fuzzer. We also have a set to store the already discovered code blocks. And then in the loop, we choose one from this set of interesting inputs. We mutate it somehow, then execute our application with it, and then we get coverage data. And if we discover that these inputs could reach those parts of the code that we haven't discovered yet, then we consider this to be an interesting input. We add it back to the queue and update the set of already seen code blocks. Most fuzzers, by default, know how to do this, but due to our special needs at input generation, we had to implement this for ourselves, which we could do, and which we did, except for one small detail. We still need to choose a strategy about how to choose an input from the queue of the interesting ones. And finally, I would like to summarize all this. Most importantly, we didn't find any bugs yet. Hopefully we will. The earlier mentioned 5+1 sections of our applications are 3 of them are already implemented, or 3 of them can already be executed in the emulator. The other 2 and the init sections are still work in progress. And we already have a lot of code to implement some system calls and do some heap initialization. When these will reach a more mature state, we plan to open source this so others can fuzz their trusted applications as well. And as I said, we almost completely implemented coverage-guided fuzzing, and we found a solution to fuzz applications that take their inputs from memory, even if this input is quite sparse in nature. And finally, I must thank to the SetIt project which financed this work. And that's all. Please feel free to ask questions.
Any questions? It's like you have none, Roland, so you're free to get on with it. Thanks very much for your presentation.
Thank you very much.